Hi folks, let's try to do today the range sum of BST again. You might ask me again, but because this time we are going to do this in C. And it's interesting that these problems can be very easily solved in Python, but at the same time, if you are embedded software engineer or you work at low level operating system kind of code, then you also have to be good at C. So, and C being a real language, I don't mean to say that Python is not a real language, but C being what the king of languages, or a kind of a language which is very useful for low level interaction with hardware, writing operating systems, and also to write the code that runs on the machine as fast as possible. It's definitely worth knowing this language if you are having any ambitions of working at the operating system or low level or device driver kind of thing. So let's try to do that. This range sum of BST in C, and let's see what happens. So what we're going to do is, I think we worked on this algorithm when we did this problem in Python. So fundamentals are pretty much the same, but what would be interesting to see is that how much of the leverage that Python gave us by having some built-in data structures is basically pretty much lost if you use C. So we'll have to see that, but let's just start by first having a queue, because first of all we would need a queue, unlike Python where we were able to okay. So before I even go there, I would like to actually read the problem again. I do not want to assume that you guys have already done the Python version of it. So the range sum of BST, given the root node of a binary search tree, which we know has some very interesting properties, these binary search trees, because everything to the left of a node is less and everything to the right of a node is higher. So return the sum of values of all nodes with values between L and R, with value between L and R inclusive. So the binary search tree is guaranteed to have unique values, which is awesome. So let's try to make our job, I guess, a little easier, and he gives us a example. An example is 10, 5, 15, and 3, 7, null, and 18. And by the way, when on Leetcode you see trees being described as bunch of values in a list, always know that they are basically printing them in a label order. So this tree would actually look like this. It's going to be 10, let's say 10, and then you would have 5, and then you will have 15 here, and then you will have 3 here, and 7 here, and then you have null, which is the left child of 15, and then you have 18, which is the right. So this is that tree which is here being written as 10, 5, 15, like that. This is label order. And then he says if L is 7, R is 15, then the sum is 32. Why is that the case? Because if you take, we get to add 7, we get to add 10, 17, and we get to add 15. So 17 plus 15 is 32. Now let's check this here, and this here is 23. Because the L is 6, R is 10, so you get to add 10, no 5, 15, this is 25. No, because R is 10. So 10 plus 7, 17, and 17 and 7, basically 1 and 6, so this is 23. Now 17 plus 7, or 17, let's do it again, I don't want to confuse you guys. So 6 and 10, so 10 is included, 5 is not, 3 is not, because the lower limit is 6. 7 is, so 10 plus 7 is 17. 17 plus 1 is 18. And 18 and 6, 18 plus 2, 18 plus 2 is 20, and then you get 4. So shouldn't this have been 24? But he's saying the output is 23, and F and L and R are included. So that's 7 should have been included. 10 plus 7, 17, plus 6, 23 already. Oh, I see. 1 is not included. I'm sorry, guys. 1 is not included. So 17 plus 6 is indeed 23. Now, other interesting things which would be very useful, actually, we'll see shortly. These things will be very, very interesting to know that number of nodes in the tree is at most 10,000. This is cool. It matters here because may have to create our own queue. The final answer is guaranteed to be less than 2 raised to the power 31. So this is another good thing. That means we can have a accumulator in a int 32. So that's good. So let's start attempting here. We would not use recursion. We would use the iteration, level order traversal kind of thing. And as you can see here, create queue, we are trying to create a queue. So let's write first in a little bit higher level. We will not implement these functions at this point, but we would just see how. So first of all, we would assume that this, he said that there are a number of nodes in the tree is at most 10,000. So we should make sure that our queue is at least 10,000. Now, what is the next thing we do? We use a temporary variable node. We call it node. So that's our pointer. Now, I'd like to write it this way. In any case, so that's and then first thing we just like the Python, the higher level logic is the same. So we say enqueue on the queue, the root node, and once you have enqueued, we also need a variable sum. Initialized to 0. Now, if root is, you can't say like Python, if not root, it's very C-like. Instead of saying root equal to null, this could also have been written as root equal to null, return sum. And so basically that is all looking good. We have created a queue, we enqueue the queue root, and now all we need to do is keep dequeuing. So while node equal to dequeue queue, and because we may want to typecast the value returned by dequeue, because I'm guessing that we are going to be implementing these enqueues and dequeues, and we don't want them to know that we are actually working on node. We might, in a very generic way, we may implement a void star. They may be storing void star. So just to shut up the compiler, we may want to do something like this. Typecast the return value of dequeue to its appropriate type on the left. Now, while node equal to, okay, that's not bad. All right, so this is we are dequeuing. We keep dequeuing the elements from the, in the beginning we have only enqueued root, and we know the root is not null. So at line 20 we enqueue root, we start dequeuing. Now what we do is, after we have dequeued, we see if node val is less than equal to L and node val is actually should have been greater than equal to L. Would it be greater or would it be less? So we want if we want the value of node to be included, we will have to do a, or if the node is between L and R, so that means if node val is greater than equal to L and less than equal to R, I think that should be our logic. So we would have to increment the value of the node, sum plus equal to node val. So this is all the beautiful C syntax that we were kind of, the Python was spoiling us by having too simplistic kind of syntax. But anyway, this is interesting. So now, having added the value of node, if it lies, we have to see if node val less, if node left and node val is less than equal to, so if node val is greater than L, we would have to pretty much enqueue node left. Similarly, if node right, we have a, so let's think about this, why that logic is required. So if we have, let's take a case where L is 4 and R is 14. Now imagine if L is 4 and R is 14, we want all the nodes whose value is between 4 and 14 inclusive. Then if we are working on a node whose value is 15, let's say, if that is the case, we know that the right side, this is a BST, everything on the right of that node will be greater. So there would be no point in basically adding the taking care going on that side on the node's right, because it's a BST, and if the node is value is 15 and we want the things between 4 and 14, we know everything on the right of that node will be greater than 15, so we would not have. But if we are in the middle, or if let's take this example where um, L is 4, again the 4 and 14, but the node's value is 10. If that is the case, the node's value will be less than 14, and it makes sense to go to the right and see if there might be nodes which are which satisfy this condition, and we may be able to get their value into the sum. So again, enqueue node right, and sorry, here syntax. Okay, so once we are done with this, we should be good to go, in the sense that we should be able to have the sum will start looking good. Then we can say return sum, and that should pretty much be the higher level logic of range BST. Of course, this code will not compile because we have not, this is not Python. We are not lucky enough to have all these data structures given to us. So we'll have to implement these ourselves, which is going to be an interesting exercise. Let's still try to run. Obviously, it's saying that unknown type name Q, so we'll have to define that. We can try to fix that. So let's try to now design a Q data structure. We would try to implement queues using arrays, and we need to see how to what that implementation should look like. So if we have, let's assume we have a data structure type dep struct q, and what would we need in a data? Let's try to design a q data structure in C. So we know that we would need, if we are going to implement queues using arrays, then we would need a front. Let us say this is a queue and we would need, so this is an array. An array has bunch of elements. Let us say this is blah 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 dot 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 dot. So if this is the array, then we know that this might be at the leftmost side will be the front. We'll need a front, we'll need a rear, and we will need the size. This is the current size, not the maximum capacity. So we would need front, we would need rear, we would need size, and we would also need an unsigned value known as capacity, and we would need an array where we are storing these tree node objects. In the C language we call them as pointers. So how do we what kind of an array we need? Can we store these tree nodes in a integer array? Probably not a good idea. So then we would need to have an array where each element itself is a pointer, and that's, I'm guessing, could be done using something like this. Basically, think of it this way, that in C, if you have a syntax like this is a pointer to an integer, but this can also be dynamically allocated to be some 100 times size of int, let us say. So in this case, P is pointing to a block of memory which is equivalent to 100 integers, and if integer is 4 bytes, it's 400 bytes of memory P is pointing to. And P0, if you have read your KNRC, you would know that P can also be treated, those values can either be treated like a star P and then a star P plus 1, like P plus 1, and that is difference, like, because this is the pointer arithmetic, so you'll get the second integer, or they could be indexed as P0, P1, because in C the pointers and arrays have a very close similarity. So in this case, now if that is the case with the integer array, imagine if you have to allocate a array of pointers, we would need to here star star, right? So if you just read it from this side, array, like example, P is a pointer to int star. So if you want a integer array, you start with int star P. But if you want a array of pointers, you start with, so you need an array of this type, the one that I highlight, wide star. So everything in that array would be a wide star. That's why we need a wide star star. So anyway, I hope that's not too confusing for you guys. Otherwise, you may have to go and read KNRC chapter. I forget. I guess it's a chapter on arrays and pointers in arrays. Similarity between pointers and array, where he talks about indexing and the indexing a pointer using either the index notation or using the pointer arithmetic. And that would become clear. So now let's write our first function, which is create queue, and it would return us a pointer to a queue, and we will call it create queue. And what that does is that it basically takes only one parameter, which is capacity. So this is the initial size. In fact, and we are not going to plan to change it dynamically, in the sense we allocate a queue. This is, we are just doing Leetcode problem. We don't want to have a very fancy queue which dynamically changes its size. So the size is kind of, capacity is fixed. So unsigned int capacity, and let's implement that. So here we'll allocate a queue data structure. So q star q, and then q equal to malloc typed abstract q. So we are okay to use q as a data type. So size of q, malloc size of q, and then we say q's, we initialize everything in that. So q front equal to 0, q size is 0, we know, because there's nothing in the queue at this point. When the queue is first comes up in live, it springs up in action. And then q rear, that's interesting. What do we want to do? Should we allocate it at the back, or should we allocate it at the very beginning? So let's allocate it at the very beginning. So my theory is that we are assuming that both q front and q rear start by pointing at the front, at the 0th element of this array, and then we say q array equal to malloc capacity. Oh, we also have to allocate the capacity to the value passed in. So we'll say here we can directly use the capacity, and now, or we can do this, times the size of, what should it be? It's a void stars. Each element of that is, because it's going to store a pointer, and we want to make that as a void pointer. So it's a size of void star, or should we say size of a star q array? And that shouldn't be too confusing. It's like saying size of a star p. If we had to do a allocation on something like this, int star star p or void star star p, then you would have said p equal to, suppose you wanted to allocate this array of pointers, you would have said p equal to malloc 100 times size of a star p. So that's where we are coming with a star q array. So here that's our q, and now we can say return q. How is that? That's looking good. So that's our create queue function, and if you run it now, it will not probably complain about create queue. So let's do that. Enqueue, now it's complaining about enqueue not being there. So let's implement enqueue. How are we going to implement enqueue? Enqueue returns nothing basically, and it takes a queue, and it takes a void star pointer, which is could be anything in this point. You can call it data or whatever the heck it is that. So how do we implement enqueue? We say if first of all in the enqueue, if q size equal to q capacity, basically the queue is full. We could have written a helper function with saying if q full, then return, but I'm just right now, maybe we should actually write that if q full. So what should be the implementation of q full? Q full returns a 1, let's say this, return, so integer q full. takes a pointer to a queue, and then it tells you the queue is full, which is very simple. All we do is return that's it. If queue size is equal to queue capacity, it will return true, otherwise return false. And what is queue empty is going to be like that. And so queue empty, are we going to implement queue empty? Queue empty is going to be, if we might implement in a similar way, we say if queue size equal to 0, then it's basically the queue is empty. So it's good to have these helper functions. They kind of make the code look cleaner. So you can, instead of doing that here, we can simply say if queue full, if queue full queue, then we just return actually. Why do we return here queue full queue? Because we are not, that's a no op for us, because you're trying to enqueue data on a queue that is full, and our queue is not going to be at this point so sophisticated that it would dynamically resize itself. So we would just return here. Otherwise, it's very easy, folks. All we need to do is we need to put this data. So we say queue front. So queue rear. I think, you know what we should do. We should be enqueuing at the rear and dequeuing at the front. So if queue rear, so basically queue array and queue rear equal to data, and then we increment queue rear, and we increment queue rear equal to queue rear plus 1, subject to, so this is incrementing of a variable subject to the constraints that it is confined to a range, and that we take care by doing a mod of the queue capacity. So queue rear equal to queue rear plus 1 mod queue capacity. That way we make sure that it never goes, the queue rear remains within its bounds. So it is it's possible for queue rear to move back to the its initial location, kind of rollback, but it would not have, basically this queue cannot have more elements than its capacity, but you can always enqueue and dequeue within that capacity. And now queue size is incremented by 1 because we did an enqueue, and so that seems to be the implementation for enqueue. Now let's do a dequeue. Now dequeue is, in the case of dequeue, there is no second variable because we are given a queue, and the return value will not be void now. It's going to be a void star. Okay, so how do we do queue? If queue is empty, queue. If queue empty queue, then we just return. And now queue array So now how are we going to dequeue? So if queue is empty, there's nothing to dequeue and we return. Otherwise, we take the value at the front. We say, let's have a variable here, void star data. And then we say data equal to, in this case, we'll be picking up from front. And then we'll be incrementing the front because we have next dequeue will be happening at the next index value. So we'll be incrementing front subject to the limitation that it should be bound by the capacity. So we have these two indices, front and rear, which are kind of going in a revolving manner around a particular piece of memory of array. And so here, and then we do a queue size. How is that? Does that look good? So here we are, enqueue, dequeue we have implemented. Do we see any issue with this implementation? Let's try to run it now. Line 53 is having issue here. So line 53 is, oh wow, so that was a problem right here. So here, as you can see, should be returning a null pointer if the queue is empty, because the return value of the function is a void star, not void. It's saying passing argument 1 of enqueue from incompatible pointer type. Let's see why that's the problem. So enqueue was the first variable of enqueue is q, and q is, what is q here? Q is this is what q is, and create q returns as a q. So let's see why in q. Q star q equal to create q. Oh, and here. So the problem was at the code line number 76. So you should be enqueuing to q, and same thing we should be enqueuing to q, not to. So next enqueue takes two arguments, right? One is the q to enqueue, another is the node. So let's see. Hold over. Oh, all right. The q. So you're saying control reaches end of non-void function. So we have not returned the data here, folks. Now hold our. Okay, wow, that's awesome. That's awesome. So it's actually accepted, and I was being a little bit careful and not being too optimistic. I was thinking that there might be some bugs in our queue implementation, but apparently that has not been the case, and our ransom BST in C with our own with a iterative implementation, not a recursive implementation, has succeeded. So let's do a submit and see if all the test cases pass, and if that is the case, we would be golden. So let's see here, q array, q malloc, front size, rear capacity, see if we have any bugs. That is looking good, and q is looking good if q full. So let's do a submit. Awesome, that worked actually, and that's an awesome news. We have just implemented a range sum of BST in C, which coming from Python, I was thinking going to be a little painful because we don't have the built-in data structures in C that Python gives us. In Python, we would have simply just used the list um, q dot append and then q dot pop to the index 0, and that would have been enough to have a queue FIFO data structure. But here we had to write our own little API. We had to provide enqueue, dequeue, create queue, and the data structure queue ourselves. But that has not deterred us from implementing the ransom BST in C, and it has been a pleasure solving this problem in C, and I hope it would help increment your understanding of the way the binary trees work, which is here. As you can see, we are using some of the properties of the binary trees to make sure to not work on nodes which we know are not going to be beneficial for our condition of being between L and R. And so apart from that, it was definitely a very interesting exercise, and I hope you had fun um, going through it. And I hope to solve more of these Leetcode problems in C. I will see you guys in the next video. Until then, adios.